Welcome back. In the last part of this second tutorial, we're going to finalize our study of the Wilson-Cowan model using the framework of two-dimensional dynamical systems. And in particular, we're now going to discuss how one can find the fixed points of this two-dimensional dynamical system and determine their stability. So just as a reminder, what we're trying to find are the fixed points of a two-dimensional dynamical system using a complementary approach to what we did for the one-dimensional dynamical system, where we modeled a single population of neurons in the first tutorial. Here we define the fixed points, or equivalently the equilibria or the steady states of the dynamical system, as the set of points where the dynamics of the population do not change. So similarly, for this two-dimensional system of excitatory and inhibitory neurons, that is the Wilson-Cowan model, the fixed points are defined as the points where the dynamics of the excitatory and the inhibitory populations don't change. So that's why we define the two derivatives with respect of the excitatory and the inhibitory population with respect to time, and we set them equal to 0. To understand how one can find these fixed points and determine their stability, we're first going to do this in a more graphical approach by considering the phase plane. Remember, the phase plane is the plane in which we plot one population, for example, the inhibitory, against the other population, for example, the excitatory population, rather than plotting the activity as a function of time. Now, to determine the fixed points in a graphical way, we remember what we learned about the null lines. Remember that the excitatory and the inhibitory null lines, shown here in the red and the blue, denoted the points where, the set of points in the phase plane where either one or the other population do not change. So the E null line in blue was the set of points where the population of the excitatory activity does not change, and similarly for the inhibitory null line. Because the fixed points are defined as the set of points where both the excitatory and the inhibitory populations don't change in time, you probably guessed that the fixed points are now defined exactly as the points where the two null lines intersect. And so this is denoted here by the 3 different circles. So they correspond to the points where the two derivatives are both equal to 0. So as we saw for the one-dimensional dynamical system, these fixed points can sometimes be stable and attract different trajectories in the phase plane, and can other times be unstable and can repel all population trajectories in the phase plane. So the question remains, how can one determine the stability of these fixed points? Of course, as we can see graphically in the phase plane, it is very clear which are the fixed points that are stable and which are the fixed points that are unstable. So the magenta trajectory in this case is stable because it is attracted, the fixed point 0, 0 in this case is stable because it attracts the magenta trajectory. On the other hand, the fixed point that corresponds to these two high values of the excitatory and the inhibitory population is also stable because it attracts this trajectory in the cyan. On the other hand, this fixed point in the middle of the phase plane is unstable because, as you see locally from the arrows of the vector field, it looks like it ends up repelling the trajectories, population trajectories around it. So how can we determine the fixed point stability? In addition to the graphical way that we just illustrated, we can also determine the stability of the fixed points using an algebraic way very similar to the one that we applied for the one-dimensional dynamical system. Namely, we have to linearize the dynamical system around a given fixed point and determine how a small perturbation around the fixed point will behave, namely whether it will blow up, explode, therefore determining that the fixed point is unstable, or whether this perturbation will actually decay in time, rendering the fixed point stable. So to see how we do this linearization, we take a look at the set of equations that describe the Wilson-Cowan system that tell us how the excitatory and the inhibitory population evolve in time. We're going to do a slight rearranging of these equations, where we take the time constant tau, e and tau I, on the left-hand side of the equation and move it to the right-hand side of the equation. So now, this is the same set of equations that I have written on the slide as the equations that we had before. We're going to slightly simplify notation, and we're going to describe all the terms on the right-hand sides of these two equations with the two nonlinear functions that we denote with GE and GI, which are both functions of the excitatory and the inhibitory population. So this allows us to summarize this dynamical system in two dimensions as in this simplified form, where the dynamics of the excitatory and the inhibitory population is described using these two nonlinear populations, GE and GI, which are given by these complex expressions that we're just not going to carry over for our next analysis. So we have a compact way to describe this two-dimensional dynamical system that represents the Wilson-Cowan model. So now the question remains, how can we use this notation to linearize the dynamical system around the given fixed point and determine the stability of the fixed point? Let's, for simplicity, assume that the fixed point is given by RE star and RI star. So we use the star, the asterisk, to denote that the excitatory and the inhibitory population are at a given fixed point. To determine, to do the linearization and determine the stability of the fixed point, we follow a similar approach to what we did for the one-dimensional dynamical system. There, we applied a perturbation around the fixed point, and we derived a one-dimensional first-order differential equation that told us how this perturbation evolved in time. This was a differential equation that we could solve. The solution was an exponential, and the sign of the exponent, the lambda, which was the eigenvalue of the system, told us whether the fixed point was stable, if the eigenvalue was negative, and whether the fixed point was unstable if the eigenvalue was positive. We do the same approach for the two-dimensional dynamical system, but here the linearization has to be done in the phase plane, so in the two-dimensional phase plane. To do this, we have to define the concept of a Jacobian matrix that effectively has us compute the derivatives of these two populations, GE and GI, these nonlinearities that we defined to be the expressions on the right-hand side of the equations on the previous slide, that effectively are the linearizations along the excitatory and the inhibitory direction in the phase plane. So very similar to what we did for the 1D system, where we just had a single population. So by computing the derivatives with respect to the E and the I population and evaluating them at the fixed point, we can obtain a numerical expression of this matrix for each of the fixed points. So as before, we can obtain then a differential equation that has solutions that are now a sum of two exponentials. And the exponents in the two exponentials correspond to the eigenvalues of this Jacobian matrix computed at the fixed point. And as before, we can investigate what these eigenvalues are to determine the stability of the fixed points. For the one-dimensional system, because we had a single exponential, the eigenvalue was always real, and it was its sign that determined the stability of the fixed point. In this case, because we have a two-dimensional matrix, the eigenvalues can actually be real or imaginary. This is interesting because it gives rise to much more interesting dynamics in the case of the two-dimensional system than in the one-dimensional system, but it also makes the analysis a bit more complicated. That's why we consider these two cases separately. First, we consider the case of real eigenvalues of the Jacobian, and then we consider the case of complex eigenvalues of the Jacobian. For the case of real eigenvalues, let us consider the example we have studied so far. So we have the phase plane with the two null climbs shown in red and in blue, and the three fixed points, two of which we know from the graphical analysis are stable and one is unstable. As you will have a chance to explore in the notebook, if one evaluates the Jacobian at each of these three different fixed points, we will see that the eigenvalues are real. So this corresponds to this first case. The two real eigenvalues, we denote them with lambda 1 and lambda 2. For the two fixed points that the graphical analysis tells us are stable, if we compute these two eigenvalues, we will find that they're real, that they are both real, and the values are negative. So this means that these two stable fixed points are known to attract trajectories in the phase plane. So indeed, that's what we saw with the trajectories that we had earlier. These fixed points are also known or called stable nodes. One can also consider a different scenario and find where the eigenvalues are real but positive. In this case, they define a fixed point that is unstable, which is known as an unstable node. We don't show such a fixed point in the example here on the right. And the last case is a scenario where the two real eigenvalues have opposite signs. So one of the eigenvalues is positive and the other one is negative. This also defines an unstable fixed point, but one that is called a saddle point. And so interestingly, if you kind of look locally around this unstable fixed point in the phase plane, you see that one of the directions is attracting, and in another direction, the trajectories end up being repelled out of this fixed point, yielding it in general as an unstable fixed point. But in addition to this scenario 1, where the eigenvalues are real, we also have a scenario where the eigenvalues can be imaginary. So in this case, it is the real part of these eigenvalues that determines the stability of the fixed points. So let us consider the phase plane, where we have now modified some of the parameters, as you will explore in the tutorial. So that now the two null lines intersect at a single fixed point. And now if we start with a trajectory that begins at this particular initial condition for the excited trend inhibitory population, we see the trajectory end up spiraling into this fixed point. So graphically, we can derive that this fixed point is stable. But what is interesting is that the dynamics with which this trajectory approaches the fixed point is very different than what we saw before. Rather than the trajectories just decaying in time or growing in time, here this decay towards the fixed point, this approach toward the fixed points, happens in an oscillatory manner. So this particular fixed point, because it's attracting, corresponds to, is called a focus, so a stable focus. And not shown here is a different alternative, a different scenario where the real part of the eigenvalues can be positive, in which case the fixed point is unstable and is known as an unstable focus. Now, just like what we did for the other types of fixed points that were nodes, where we didn't have this oscillatory dynamics, we can also visualize this trajectory in the activity versus time plane. So here we plot the excitatory and the inhibitory activity as a function of time, and what is shown by this spiraling in trajectory in the phase plane is illustrated by this oscillatory dynamics in the activity versus time plane. So each of the two populations oscillate in time, and their amplitude decays in time because this fixed point is attracting. If the fixed points were repelling, then what we'll see is oscillatory dynamics with amplitude that grows in time. Now, in two-dimensional dynamical systems, in addition to fixed points, we can also get other types of equilibria or steady states that are not fixed points. So these are sort of more interesting and relevant for different concepts in neuroscience. And one such equilibrium is a limit cycle. So in this case, we can visualize the limit cycle in the phase plane by considering, say, two trajectories, one in the black and one in the yellow. And so we see that the two trajectories don't converge or get away from a particular fixed point. Rather, they converge towards this limit cycle shown here in the cyan. So if we look at this in the activity versus time plane, and before we show that, let's just conclude that these limit cycles, just like fixed points, can be stable or unstable. So here we see a limit cycle that is stable or attracting. They can also be, of course, unstable and repelling. But we can also look at them in the activity versus time plane, and we see that they are characterized by the fact that they generate these oscillations with fixed and steady amplitude. So unlike the focuses that we showed earlier, where the activity oscillates but with a decaying or a growing amplitude, here, in the case of the limit cycle, the activity oscillates but with a fixed amplitude. So indeed, we have finished our study of the dynamics that can be generated by these coupled populations of excitatory and inhibitory neurons, known as the Wilson-Cowan model. We have shown in the last few sets of slides of this tutorial how to find the fixed points, how to determine their stability, how to visualize the activity in the phase plane, but also in the activity versus time plane. And in the tutorial, in a moment, you will have the opportunity to calculate the fixed points, numerically evaluate the Jacobian matrix at each of the fixed points, and determine the eigenvalues, which will then determine the stability of the fixed points. You can also change some of the parameters in the Wilson-Cowan model and look at when limit cycles emerge. If there's time, you can also study the implications of some of the dynamics that we have modeled with this Wilson-Cowan model in a more biologically relevant scenario, for example, the generation of working memory.